I think you prefer English to French.
Yes.
Donc on se réunit, I have to start in French, sorry. On se réunit aujourd'hui pour écouter la thèse de Antonello et pour lequel je propose about something like 45-50 minutes for the presentation before I give the floor to the jury for some questions. And so, whenever you're ready.
Okay, thanks. So, hello everybody. Before starting, I would like to thank all of you for coming here to my PhD thesis defense, especially the jury. And I would like also to thank Antonello, who has supervised my work during these 3 years here at Saclay. And so you can read here the title of my PhD project, and this is about a particular type of galaxies that are called the starburst. I will give the exact definition later, but here I want to say that starbursts are among the most luminous star-forming powered galaxies in the universe. And for this reason, they are the first studied objects at all redshifts and all possible wavelengths. And what we want to do in this thesis is to understand the properties of these galaxies, and in particular to understand whether we can extrapolate from their properties also those of less luminous star-forming galaxies, or whether they are instead a special population that has to be treated separately. Indeed, there are some works in the literature that claim that they are mostly merger triggered, while other studies claim that they are just normal galaxies but with a higher content of gas, and so for this reason they form more stars. And so let me go into all of this with more detail, and let me start from a very basic knowledge about galaxy evolution and properties. So if we plot the color versus the stellar mass of galaxies in the local universe, we can see that they follow two main regions. So the red sequence here is populated by passively evolving red elliptical galaxies, while in the blue cloud reside galaxies that are actively forming stars at present. And the star-forming galaxies also follow a very tight relation between the star formation rate and the stellar mass, which is called the star-forming main sequence, while red galaxies are situated systematically below, with much lower star formation rates. But an important discovery is that these two diagrams are not the same at all redshifts, but they tend to evolve as we go at earlier epochs. And this bottom panel shows you the evolution from redshift 0.1 to about redshift 2 of the color mass diagram. This comes from simulations by Trayford et al. 2016. And we can see that the galaxies become on average bluer in the past, but also that most of the galaxies were residing in the blue cloud at redshift 2. So an important consequence of this is that galaxies have to evolve, and so they have to go from the blue cloud to the red sequence as we approach to the local universe. This means that many galaxies become passive as the time goes on. And we may wonder what is the physical mechanism that is responsible for this huge transformation of galaxy properties. So in order to answer to this question, we can look a bit more in detail about star-forming galaxies, because they are not a homogeneous population. Indeed, there are the majority of them that follow the star-forming main sequence, like our Milky Way here, but there are also some systems that have star formation rates systematically above this relation. And this is what I call starburst. So in my work, I will define starburst as those galaxies with a star formation rate a factor of 4 higher than the star formation rate of the main sequence at the same redshift. This basically comes from the definition by a work of Rodiger et al. 2011. And this type of galaxies, the majority of them are also highly luminous in the infrared. For this reason, they are called also LIRGs or ULIGs, which means ultraluminous infrared galaxies. And in the local universe, they seem to be a special population. This is a collection of images of some ULIGs in the local universe, and they all appear to be interacting or merging. And so this peculiar property triggered a lot of studies in the past 30 years, both from an observational and theoretical point of view. This is a collection of some of the most important studies about this topic. And from here, basically, we learned that URIPs are mainly triggered by major merger events, and they may represent the missing channel between spiral galaxies and elliptical galaxies. So the merger is a very powerful mechanism that is able to quench star formation and make a galaxy passive. Another important property of these URIPs is that they are on average very dust obscured. So the dust has the effect of absorbing the UV light from young massive stars and re-emit this energy at infrared wavelengths. And sometimes this process is so extreme that we cannot even see the galaxy in the ultraviolet and optical wavelengths, while we can only detect them at longer wavelengths, for example in the near infrared and in radio. This is ARP 236, is a representative URIC in the local universe. And because of this huge dust attenuation that we find in these systems, it is very difficult to study this type of galaxies, especially at higher redshift, where indeed there is a strong debate on whether high redshift starbursts they are still triggered by major mergers, like in the local universe, or they are just due to a higher gas fraction, so perhaps to anomalous gas accretion events, like claimed by some other works. And this question is not really trivial, because a recent paper by Fench et al. 2017 claimed that mergers are not anymore able at redshift 2 to enhance the star formation rate of the system. And in order to solve this long-standing debate, we may naively think to look at the morphology of the galaxies, and so to see directly whether they are mergers or not. But the morphology is very unreliable as we go to higher redshift because of the decrease of the surface brightness of galaxies and also the decrease of spatial resolution. And so we can instead look at two other physical properties of the galaxies that are less affected by this increasing redshift, that are the dust attenuation and the metallicity of the starburst core. And this can be used to test the merger scenario. Because the dust attenuation, for example, we expect that from a merger scenario we have a very dust obscured optically thick core that you cannot create just by a gas accretion event. And also, if we are able to find an enhanced metallicity in the core, this will trace the enhanced star formation efficiency, which is expected by a merger scenario. And so a first tentative investigation of these crucial questions was made by Pugliese et al. 2017, of which I am a co-author. And here basically we selected a sample of Herschel detected starburst at redshift 1.6, and we investigated the dust attenuation properties of this sample. And we discovered with the stacked spectra that the dust attenuation inferred from the Balmer decrement, so from H alpha and H beta, is much lower than what is inferred from the infrared luminosity. And this discrepancy between the dust attenuations was reconciled by assuming a two-component model for starburst, which is shown here. So starbursts are thought as made by an optically thin layer in the outer region, which is responsible basically for all of the optical emission line, but it accounts only for about 10% of the total star formation rate of the system, while there is an optically thick core which is responsible for 90% or more of the total star formation rate, but is basically invisible at optical wavelengths. And in this case, we could also only put limits on the dust attenuation of the core, and it was clear that we could not constrain the metallicity of the central region of the starburst, because basically the optical lines only trace a very small fraction that is not representative of the whole system. And so the idea here of my PhD thesis was to push this study at longer wavelengths, so to use near-infrared rest frame spectra to study the properties of these galaxies. And the motivation is that the dust attenuation is lower at near-infrared wavelengths. For example, Paschen beta is expected to be 20 times less attenuated than H alpha in case of strong obscuration. But there are also other important motivations of this analysis. So first of all, there are no surveys that have yet tried to systematically track near-infrared lines in all type of galaxies, and only small sample exist in the local universe. But it is also important for future JWST observations, because this instrument, this telescope, will be able to observe near-infrared lines at much higher redshift and at much fainter levels. And so we needed, in order to fulfill all these tasks, a well-defined and robust observing strategy that is highlighted here. So we basically proposed and get observing times with these three different instruments: FIRE at the Magellan Telescope, and then CMOS and MOIRCS at VLT and Subaru. But why did we need all these different kind of instruments? Well, the reason is that all of them have different features. For example, Magellan FIRE is a single-slit eggshell spectrograph with a very large wavelength coverage and a very good resolution, but you can only observe one object per time. And so we dedicated this observing time to observe starburst galaxies, as many as possible, because they are the main target of my PhD work. While CMOS and MOIRCS will be used to add the main sequence galaxies to the analysis, to increase the statistics. And I should say that I have not finished yet to exploit all this rich data set, and indeed my PhD thesis is entirely based on a subset of 25 starburst galaxies that were observed with Magellan FIRE. So I will focus on this now, and these galaxies were selected according to these criteria from the Super Deblended catalog published by Chin et al. In 2018. And we asked the starburst to be infrared detected, to have a stellar mass higher than 10 to the 10 solar masses for completeness reasons, and a secure spectroscopic redshift between 0.5 and 0.9, because this allows to detect both H alpha and Paschen beta in the spectral coverage of FIRE. And I should say also that we didn't bias the sample against any particular morphological property, or we didn't put any constraint on the dust attenuation, any prior knowledge. So we can say that this is a fairly representative sample of starburst galaxies at about redshift 0.7. And after the observations that took place in two observing runs in 2017 and 2018, I spent several months to reduce the spectra, to calibrate them, and to fit the emission lines. And this is just a highlight of all the emission lines that I could be able to detect in the spectra. They range from H alpha and hydrogen 2 in Y and J band to Paschen beta and iron 2 in K band. And so after describing the observations, I will now move to the main scientific points of my thesis that I addressed during these 3 years. And the first question was to understand the origin of starburst galaxies at high redshift. And then after establishing a connection between starburst galaxies and mergers, since mergers are by themselves long processes that can last for 100 million years to 1 gigayear or more, here the idea was to connect the merger phase to the different properties of the galaxies. While in the last part I focus instead on the effect of mergers on the galaxy morphology on the smallest scales. And so to this aim I performed a systematic analysis of morphological parameters and clumpiness in large samples of galaxies, both starburst and main sequence systems. Okay, so let me start from the first important question of my PhD work. And if you remember, I said before that the dust attenuation is a crucial parameter to test the origin of starburst galaxies at high redshift. So this is the first property that I wanted to explore from this subset of 25 starburst galaxies observed with Magellan fire. And so I plotted here on the x-axis the observed ratio between Paschen beta and H-alpha lines, while here on the y-axis this is the attenuation at Paschen beta that is inferred by comparing the star formation rate from the infrared luminosity and the star formation rate inferred from the Paschen beta observed luminosity. So these two axes are basically two independent dust attenuation indicators. And I came up with this picture, so I discovered that the location of this point was completely new and very surprising, because they are not in agreement with the typical attenuation recipes like the Calzetti and Cardelli law that are shown here, that are followed by the majority of star-forming galaxies, both at low and high redshift. And after some brainstorming and some thinking about possible interpretation for this particular location of our galaxies, I realized that a geometrical dust model that could convincingly reproduce the trend of these points is a mixed model of dust and stars, which you can see that can well fit the points. So the mixed model is represented by this red dashed line. A mixed model is basically a model in which stars and dust are homogeneously distributed inside a volume, like shown here. This is in contrast with a typical foreground dust screen that is followed by the majority of star-forming galaxies, is the case shown below. And then I developed the full formalism of this mixed model that I don't have time here to explain in detail all the mathematical steps, but the important point is that the mixed model depends only on a single parameter, that is the dust attenuation towards the center of the system. And you can see here that we can convert this A Paschen beta Rx through a non-linear relation into an AV of the galaxy towards the center. And another important discovery was that our galaxies, they have attenuations which spread along a large range of attenuation values. So AV here goes from around 1 to 30 magnitudes with an average of 9 magnitude, which means that V-band photons are suppressed by a factor of 4,000. And so these are really high dust extinctions that are significantly higher than what is typically found in main sequence star-forming systems that are drawn here with an orange dashed line. And so because of this, we argued in an APJ letter in 2018 that this really high, extremely obscured core found in starburst, they are by themselves a striking evidence for a merger-merger origin of these objects, because we don't know actually other possible mechanisms that are able to explain such high obscurations and optically thick cores. And so after that, I also looked at the morphology of the galaxies, which gave almost consistent result. Indeed, from a catalog published by Kartaltepe et al. 2010, the majority of our subset are classified as mergers from a visual inspection. But because of the limitations of the morphology that I have told you about before, we have good reasons to think that the fraction of mergers might be actually higher than this. So it might be close to 90% or even 100%. Okay, so after, in the second part of my thesis, there was another question that was puzzling me. So if we see here, we can wonder why these galaxies they follow almost perfectly this prediction by a mixed model, and why they have such a large range of attenuation properties. And so is it by chance, or is there a physical mechanism that is guiding this variation of the attenuation? And so in order to answer to this question, I also looked at other physical properties of the galaxies, and I discovered that there is not just a sequence of dust attenuation, but there is also a sequence of many other physical properties that are tightly correlated within each other. And these are the radio size, the nitrogen 2 over H alpha ratio, the line velocity width, and the equivalent width of all Balmer and Paschen lines that we have in our spectrum. And so I don't have time here to discuss in detail about all the correlations, but I will just show the most representative ones. Like this is the correlation between the radio size and the dust attenuation, in which we can see that more obscure the galaxies, they are more compact, they have smaller sizes. And the compactness is naturally linked to the phase of the merger, because the merger initially it has a pair of galaxies that and in most of the cases we are not able to blend them in radio with VLA, and so they just appear with a larger radius. While in the latest phases of the merger, after the coalescence, we just have one single entity, which is the merged nucleus. And another important correlation is that between the dust attenuation and the nitrogen 2 over H alpha ratio, also called the N2 index. And we can see here that more obscured galaxies and also more compact systems, they tend to have a higher nitrogen over hydrogen abundance. And for normal galaxies, we would think that this is due to the effect of an AGN. But we think that in our case, this is very unlikely, because if the AGN is in the center of the system with an obscuration of 9 magnitudes or more, it will be basically impossible to detect any emission from this central AGN. And so since optical lines, that are these two, they only trace the external regions of the starburst core that are less affected by dust attenuations, we thought that a convincing explanation for this increased N2 index is instead the shocks. And indeed, we plotted the BPT diagram for a small subset of galaxies for which we also had O3 and H beta emission lines from ancillary optical spectra. And the location in the BPT diagram of these galaxies is consistent with the predictions of shock models by, for example, Rich et al. 2011. And from a physical point of view, an increased shock contribution can be due to the fact that these systems are approaching virialization after the merger episode, and so part of the gravitational energy of the interaction goes into kinetic energy of the gas, and then to the shocks which create this enhanced nitrogen 2 over H alpha ratio. And okay, so in a paper that we published in 2019, we showed in detail all of this correlation, and we explained all this one parameter correlation sequence as a time evolutionary sequence of merger stages that is summarized here by this image. Here you can see the trend, the behavior of different physical properties as a function of the merger state. So from the pre-coalescent starburst to a coalescent starburst phase. And but we can also wonder what happens to the merger after the strong starburst phase has ended. For example, there are some works claiming that the merger can fuel a central AGN, and this AGN can later blow out the surrounding gas and stars and form a quasar system. This is a classical paradigm illustrated in Sanders et al. 1988, for example. And after the merger, also the starburst core might become an elliptical galaxy according to the classical merger starburst paradigm for example, by Hopkins et al. 2008. And so in order to investigate all these possibilities, I plotted here the size of the galaxies versus the stellar mass, because we know that different types of galaxies, they occupy different regions in this parameter space. For example, late-type galaxies are here in cyan, and while early-type galaxies, they have smaller sizes, and they are shown here with a blue line. And what we interestingly found is that our 25 Magellan starbursts, they are very compact, and 50% of them are even below the relation of early-type galaxies. And the consequence of this is that such a starburst core cannot directly produce elliptical galaxies at the same redshift and below. And so we claimed in the paper published in 2019 that instead there could be an evolutionary connection between starburst galaxies at redshift 0.7 and the bulges in spira and lenticular galaxies, because you can see here that the sizes of these objects are similar to those of bulges studied by a paper of Graham and Worley 2008. And as far as the AGN is concerned, we tried to look at all possible AGN tracers among our sample, and we discovered that a subset of 12 galaxies, we detected the mid-infrared dusty torus from CD fitting, and for a subset of 6 galaxies of them, we also detected them in X-rays. And these X-ray emitting galaxies are shown here with the big black crosses. And the curious thing is that all of them are below the early type galaxy relation. So they are likely found in the latest stages of the mergers. And so this suggests us that we might be approaching the final blowout phase that is predicted by the standard AGN merger paradigm. And so let me move now to a different, slightly different topic, but that is still connected to what I have shown before. That is the effect of mergers on the galaxy morphology. So why did I move to this topic? First of all, the morphology of the galaxy is something that I have not yet fully investigated in my sample. And also the morphology of the galaxies is an information that we have available for basically all the parent sample of both starburst and main sequence systems in the whole cosmos field. And so we have a lot of statistics to well study the morphology of the galaxies. But the crucial idea for this further work came when we realized that a representative sample of starburst galaxies in cosmos field, they not only were looking as more interacting and merging compared to main sequence systems, but they also appeared more clumpy. Like you can see here some representative cases of clumpy galaxies. And clumps, with clumps I mean concentrations of young stars that are embedded in a smoother luminosity profile of the galaxy, and they typically have masses between 10 to the 7 and 10 to the 9 solar mass, and sizes ranging between 10 and 1000 parsec. And clumps are really important to understand the galaxy evolution, because there are some works showing that they might be progenitors of globular clusters that we find in the local universe, but they might also contribute to the formation of a central bar or to the bulge growth that later can help to stabilize the disks and to give the final imprint of the morphological Hubble sequence that we have in the local universe. But despite this importance, their origin is not yet fully assessed. Indeed, there is a strong debate on the formation mechanism of these clumps. There are many studies, especially at high redshift, that attribute the formation of clumps to gravitational instabilities of gas-rich turbulent disks. But there are also other works that claim that mergers can have also a huge impact on the formation of these structures, like in the paper of Puech 2010, based on a sample of 11 clumpy galaxies at a redshift of about 0.7. And so I thought that I have the perfect sample to investigate this problematic, because I have a lot of statistics in the full cosmos field and a lot of galaxies in a large range of stellar masses and also of redshift between 0.5 and 0.9. That is the same range that I have investigated before in my PhD work. And but in order to study in a robust and quantitative way the contribution of clumps to the galaxy emission, we need to define this clumpiness quantitatively. And so this is done through the clumpiness parameter, which is defined here. And this is basically a ratio between the flux that resides in identified clumps divided by the flux in the whole galaxy. And the clumps were identified through this multi-step process that I don't have time to explain all of this in detail, but we think we have a quite robust estimation of this parameter. And with the clumpiness, then I investigated the distribution of it among starburst and main sequence galaxies, and also among visually selected mergers and not merger systems. And the results of this analysis is summarized in this slide with these three diagrams. And in the first one, we can see that the starburst galaxies that are shown in red, they tend to have a higher clumpiness compared to main sequence systems shown in blue. So here I took 100 starburst galaxies in cosmos field that are all the starbursts identified, and I compared them to 160 main sequence systems with the same mass distribution. And so they were selected randomly among like 2,000 main sequence systems found in the whole field in this mass and redshift range. And another result is that even visually selected mergers among the main sequence, which are represented in this histogram with a cyan line, they tend to have a slightly higher clumpiness, but still significant, compared to isolated main sequence galaxies. And finally, we also find a nice correlation between the clumpiness and the distance from the main sequence for visually selected mergers, as shown in this other diagram here. And so from all this diagram, what we claimed in a paper that we have recently resubmitted to A&A is that they all indicate that mergers likely have an important role in enhancing the clumpiness of the galaxies. So they might really induce clump formation at least at redshift of about 0.7 that we are investigating here. And then we also confirmed this scenario of merger-induced clumps formation with the numerical simulations that were kindly performed by my collaborators, Jeremy Fench and Frederic Bourneau. And the results of these simulations are summarized here. And in these two diagrams, you can see the trend of the star formation rate and the clumpiness as a function of time for three different types of simulations. So the orange and the blue line are two simulations of galaxy disk collisions at redshift 0.7, and so with gas fraction of about 0.3, which is typical of this redshift, while the black line is indicative of a single isolated disk galaxy. And the difference between the blue and the orange lines is just a different orientation of the rotational spin of the two colliding galaxies. And the main result that we can see here is that in the starburst, during the starburst phase of the merger, we have in the blue simulation an enhancement of the clumpiness up to values that are similar to those observed. And but an important point of this simulation is that the degree of enhancement of the clumpiness also crucially depends on the geometry of the interaction, and in particular in this case on the orientation of the rotational spin. So for example, in a retrograde merger, that is the orange line, which basically means that the two galaxies are rotating in a direction which is opposite to the encounter direction, we have a lower increase of the clumpiness compared to the first case. And so finally we could also reproduce with simulation the correlation between the star formation rate, or the distance from the main sequence, because here the mass is fixed, and the clumpiness for visually selected mergers. And this correlation is shown here with the colored circles. And so after this, I would like also to mention some future developments of my thesis. And as I told you before, we got data from KMOS and MOIRCS, and we managed to reduce part of the sample. So these are just some examples of galaxies that were fully reduced and calibrated. And so, as said before, this data will be used to observe and apply this analysis also to main sequence galaxies. And in particular, I will look I will try to find calibrations of the metallicity with near-infrared lines. And in particular for KMOS we can do even something more, so we can look for radial gradients, for example, of the attenuation and the metallicity, or even test, look for evidences for rotation. And I have already started to explore the near-infrared lines with some cloudy models, and the results are quite encouraging. Indeed, as shown here, I found that it would be possible, in principle, to track the metallicity of the gas in these galaxies thanks to the sulfur 3 over Paschen beta emission line ratio. And these cloudy models also suggest that we might be able to separate the starburst and AGN excitation through only near-infrared emission line ratios. And so the advantages of these emission lines is that, of course, they are much less affected by dust attenuation compared to the most used optical tracers. But this is still an ongoing work, let's say. And finally, we also are getting data from NOEMA. We have just resubmitted a proposal to increase the size of our sample, and the main role of these NOEMA proposals are to test star formation rate timescale effects on the dust attenuation. Indeed, as said before, the dust attenuation was derived by comparing the infrared luminosity to the luminosity of the lines. which of course they trace different timescales of star formation, like 100 million year for the infrared and 10-20 million year for the lines. And so in order to probe possible timescale effects, I will use the CO flux, and so to derive the CO luminosity and compare it to the luminosity of the line. And this should give us a more realistic attenuation value. Afterwards, we can also test the attenuation size relation that I have shown you before. And this is important because the radio sizes that I have used so far, they might be affected by the influence of an AGN, which can make us underestimate the true size of the galaxy. But in any case, the CO size will be a more direct tracer of star formation compared to the radio. And so before moving to the conclusions, I would like to show here the list of papers that I have written in this 3-year PhD period. And in particular, the first one published in 2017 during my first year of PhD. It was actually started during my master thesis with my former team. And of course, I didn't have time here to talk about this. And so with this picture, I would like to summarize the main scientific results that I obtained during my PhD thesis. So first of all, I found that a connection between the starburst and mergers is likely in place also at high redshift, at least up to redshift 0.9. That is the limit of my study here. And then I also found nice correlations between the attenuation and several physical properties of the galaxies that I explained as an effect of a time evolutionary sequence of merger stages. And afterwards I also suggested a possible evolutionary sequence between the starburst core at redshift 0.7 and the bulges in spiral and lenticular galaxies at the same redshift and below. And finally, I also studied the effects of mergers on the galaxy morphology. And what I claimed in the last paper is that mergers likely have an important role in enhancing the clumpiness of the galaxies at a redshift of around 0.7. And so where do we go after? Of course, there is GWST, which will be launched in 1 or 2 years from now, and this will be important because it will allow to increase the statistics of our analysis, and in particular to push all this study to higher redshift, even 5 or 6, close to the reionization epoch. And in particular, it will allow to track near-infrared lines down to very faint levels, and in principle, to be able to measure the dust attenuation and the metallicity in the large samples of starburst and also main sequence systems. And then, of course, there is also SPICA, which will be launched not earlier than 2032, and this will be important to study the coevolution between AGNs and host galaxies. Indeed, the SPICA will be sensitive to the mid-infrared spectral range, where we found many AGN-powered emission lines. And finally, I would like to thank you for your attention.